not actually see it on YouTube, as in like it's hard to find with a problem name. So I just have a new video. Let's see what the problem says. It's a very good problem for you to understand one very important concept. I'll specifically focus on that concept when I will teach or basically tell that concept. Now, you are given a zero indexed array, which is a 2D matrix, a 2D grid of size n cross n, and you can see it's a simple grid of size n cross n. Okay. Now, where r comma c represents a cell either containing a thief, which means a 1 value is a thief and a 0 value is the basically empty position, empty cell, 0, empty cell. In the very beginning, I will start off from the extreme topmost left corner, right, which is they're mentioning as 0 comma 0, right. Then they next say that you can move on to any of the adjacent cells. What they define as adjacent cells, they have defined all the 4 directions, left, right, up and down. They have defined as the adjacent cells. Okay, so we know that there is simple adjacent cells movement which we will do now. Okay, great. The safeness factor they have defined on a path grid is defined as minimum Manhattan distance from any cell in the path to any thief in the grid. Let's see firstly only this line. What is the safest factor? If I ask you that if this is the path, and the path is fixed, in that path, the minimum Manhattan distance, as you can see for this cell, for the thief is here and here, thief is here and here. For this cell, the thief distance is, again I'm saying Manhattan distance. You can see how they define the Manhattan distance, right? But for this cell, the Manhattan distance is 3. Okay, for this cell, the Manhattan distance with this thief is 2. For this thief, it is 4. 1, 2, 3, and 4. Okay, and same way I will compute the Manhattan distance of every cell in the path to its nearest thief, which is saying the minimum Manhattan distance for that specific cell to the thief. And out of all those Manhattan distance, I will take the minimum Manhattan distance. That will be the minimum Manhattan distance of the path itself. So first operation, find the minimum Manhattan distance of a cell. Okay, for this cell, it is 3 and 3. And same way, go and find the minimum Manhattan distance of every cell. Now, when you have found, okay, for this cell it is 3, for this cell it is 2, for this cell it is 3, for this cell it is 2, for this cell it is 3, and so on and so forth. Then when you have found all the minimum Manhattan distance of every cell, then go and find the minimum out of all these cells in this path. Out of all these cells, what is the minimum? Minimum is 2. So that will be called as the minimum Manhattan distance of this path. Got it? Okay, that's a very important concept and people get confused a lot on this. Now, last is that return the maximum safest factor of all paths leading to this end cell. So again, this is just one path which we saw, and let's say we have found out what is the safest factor of this path. Okay, then there can be multiple such paths. As you can see, I can have this path also, this simple path also, I can have this path also. Now, whichever path gives you the maximum safest factor, that will be your answer, or that maximum safest factor will be your answer. And you know the safest factor, how you will compute? Firstly, you will have to compute the minimum Manhattan distance to every of the thieves, and then for that specific path, the minimum out of all those cells will be its safest factor. And you have to maximize this safest factor, right? There are 2 minimum and 1 maximum. That's the reason I told you that it can be confusing. Now, coming on, let's summarize our maqsad. Our main aim was to maximize what? Safest factor. Again, when you have to maximize something, which means in very naive way, what you will do, okay, you will say, Aryan, I will try for a safest factor of 0, then I will try for 1, then 2, and so on and so forth. I will keep on trying. Okay, up till what point? That's a question mark. But if I see very carefully, safest factor is the minimum distance. Okay, even if I maximize that distance, what can be the maximum distance? This. Okay, for this cell, I know I will have to start. I will have to start. So what if this cell, like I can again, Aryan, what if the thief is here? Okay, if the thief is here, then I can just say this will be here. Okay, Aryan, what if the thief is in the mid? Okay, nearly I can say that in O of n plus m, I can no way, like I can for sure reach my thief. If I have one thief, in my matrix, I can, in n plus m, I can reach my thief, or n plus n, I should say. Okay, so technically, I can say n or m, or nearly around that, n plus m, but still, we can actually also compute specifically, which we will do later on, but I'm just talking about the rough thing. Roughly, it will be n plus m at max. Okay, now comes the, again, I have to maximize what? This safest factor, which means, okay, I'm trying for all the safest factor, but safest factor itself was minimum Manhattan distance to the thief from the path. And again, for every point, I will compute the Manhattan distance, which is the minimum Manhattan distance to the thief, and again take the minimum of all those cells, and that will be a minimum Manhattan distance for the path. So again, if I specifically break it down for every word, I have to maybe work around for a path. I have to maybe try for every path. Now, trying for every path itself gives us a hint of maybe we can try, again, traversal of a path. Path, traversing, trying for every path. It is simply a BFS or a DFS traversal starting from this specific node. And I know I have to try for different path. But different path for what? Different path for this specific safeness factor. So, okay, let's say I'm saying Aryan. So, you are saying that you will try for some XYZ safest factor. So, Aryan, you are saying that you will try that starting from this cell. Is this safest factor of X possible or not to reach to my end cell, which is n minus 1, m minus 1, or I can say n minus 1, n minus 1, because both n and m are same. So, now my question is, starting from this cell, ending onto this cell, is it possible to try and traverse this entire grid considering the safest factor is X? Make sure to remember what is the definition of safest factor. Now, okay, which means I still like have to figure out what all things I will require to traverse, because see, traversing in the grid, okay, but maintaining the safest factor is a question. So let's see that what all we require. So okay, we realize that we can have different paths, and I will have to start from this specific path, but still this says that if I traverse in a path, I will have, okay, for that path I have to grab the minimum Manhattan distance, which means for a specific path, let's say this was the path, I should know what is the minimum Manhattan distance for a cell. For a path, we remembered, for a path minimum Manhattan distance, we need to know the minimum Manhattan distance for a cell. So I realized, okay, for a cell specifically, I should know what is the minimum Manhattan distance. Then I realized what that was the nearest distance to its thief. So for this cell, I need to know the nearest distance to all of its thief. Because that will give me, okay, which thief is the nearest, and the nearest thief will be my minimum Manhattan distance for that specific cell, and we are finding it for the path, right? Okay, now then we technically found out, okay, minimum distance from one cell to any other cell. How we find out? By simply a level wise traversal or a BFS traversal. So we know that, okay, for this cell, to know the minimum distance, because minimum is the, okay, level wise traversal, we traverse as much as possible. In one level wise traversal, we traverse in both the directions. Then here I'll again traverse, okay, one level done. In next level I will reach here. So I would easily know that, okay, I'm doing a level wise traversal in the shortest distance. I will, again, for the shortest path, you might also think of Dijkstra's, but that's an overkill. With a simple BFS, you can already do it. So we realize, okay, with the simple BFS traversal, we can simply reach and find out what is the, for a specific cell, what is the nearest thief, which will give me, for a specific cell, for one cell, I will do a BFS traversal to know that who's the nearest thief for him. That will take a O of n into m time. I have to perform this for every cell, because you remember, you are trying to choose a path, but you will choose a path on the basis of that for a cell which I am choosing in a path, what is its safest factor. So technically you will have to find the safest factor for every cell, every zero cell I should say. So in worst case, or maybe in average case, I will have n into m cells. I will apply the same BFS for all m into n cells. So this is for one cell, for n into m cells, it will become a n into m into n into m, which just for finding the shortest path, or just to find the minimum Manhattan distance of every cell, you will get TLE. first step is how you will improvise to just find, again, your only task right now is to find the minimum Manhattan distance of every cell. Then we realize, okay, this is a very important concept. So earlier what we were doing, we were trying this for every n into m cell, right? That's the reason we were getting a TLE. But maqsad kya tha apna? Our main aim was that I have to reach this specific thief, and everyone, maybe if I try for this cell or maybe try for this cell, everyone is trying to reach to all these thieves. So why not start with the thief itself? This is a very important concept. This is a concept which I was talking about in the very beginning, that you should remember that if you're trying for all the nodes to the destination, traverse reverse, traverse from the destination to all the other nodes, right? What I mean to say is that earlier what I was doing, okay, from this cell I was trying to go to the thief, okay, and same way for this cell I was trying to go to the thief, okay. But now when I will do a BFS traversal from the thief, then in just by its traversal itself I will go on to here also and here also, and same way I will keep on going. And again, it is now just simple saying, earlier I was doing a BFS traversal from a simple normal node grid 0 to my thief, and that I had to do for every cell. But now I will do, okay, from my thief I will do my simple BFS traversal and reach, and say that, okay, for a specific grid node, how early I can reach from my thief. That will tell me the minimum Manhattan distance for that cell to the thief. Again, it can be any thief. I just want minimum distance. So I realized that, okay, I can have n again, but Aryan, what if you have n into m thieves? Bro, I'm just doing a group like multi BFS traversal. If you have not watched, just write multi BFS traversal by Aryan Mittal, you'll get the video. But it simply says that in the queue, I will push in all the 1 cells in the very beginning itself. I will push in all the 1 cells, and then parallelly I will keep on doing BFS parallelly. Okay, in the first level, what will happen? In the first level, let's say this is a thief. In the first level, what will happen? He will go on to the neighbors. And same way, in the first level, this is happening. In the next level, these will go on to its neighbors. Okay, in the next level, these will go on to its neighbors. So this is how a multi BFS traversal works, that you are actually going on from a cell to all its neighbors, and that is repeating parallelly for all the cells, like for all the thieves. So with the help of multi BFS traversal, we realize that we can just start from the thieves and ultimately find the shortest distance to all the nodes, and that can be achieved in O of m into n time, because for sure the grid size is O of m into n. Again, it is O of n into n, but I'm just showing you for simplicity or for more genericity. Now get back to the main problem. We left the problem, again at this point we left that by saying that we have to find and try for different possible paths. We also mentioned that we will try for a safest factor of x. Now when I was trying for a safest factor of x, I meant that I will start from this specific cell. I have to traverse a path. Now path traversal can be done by either BFS or DFS, that's simple, and reach this. While traversing a path, I should make sure that this cell should follow the safest factor which I have taken, x, which means again, what do you mean by safest factor of x? If I say the safest factor is x, which means that distance to thief from a specific cell, distance to thief, it should be more than equal to my safest factor, which is x in this case. But Aryan, what does it mean and how you reached here? Simply, bro, you will try and traverse. Again, this is simple path traversal. You know that you will try traversing from this specific cell, which is the left cell. Then you will simply go on and try for the next cell. Again, you are just simply your aim is to ultimately reach on to the last node. Try for any path. So either if you do a BFS or DFS, what do you do in a simple BFS or DFS? Simply try for next cell, any cell. You will try for adjacent cells. Then, okay, again try for adjacent cells. If I would have asked you, bro, this is an obstacle, this is an obstacle, this is an obstacle, like simply replace this as an obstacle. Say this is an obstacle. Obstacle is saying that your task was safest factor should be x. Let's say safest factor, they are saying it should be 2. Okay, say if the safest factor is 2 and let's say I'm traversing, I should make sure that I cannot visit a node whose safest factor is less than this assigned thing. Okay, I can be here. I can be here. If I'm traversing this entire matrix, let's say I can be here. I can be here because as you can see 1, 2. So safest factor is 2. I can be here because the safest factor with this is 1. And because I have assigned this distance to thief matrix, how it is made? It is made by simply using the previous traversal, which is the multi-BFS traversal, which we did from thieves. From thieves, we have assigned what is the distance to all the other nodes, which is the minimum distance that we achieved by multi-BFS traversal. Now, when we've achieved this specific thing, we can simply go and traverse, simply do a simple traversal and check at every step. Is this distance more than what factor I'm consuming right now? My factor is 2. So this distance right now is 2. Okay, I'm good. I will try to go forward, but this is now an obstacle for me. So it is an obstacle. Why obstacle? Because its distance, its cell distance is actually 1. And I'm only assigned 2, which means if I'm assigned a safest factor of 2, which means I can try for a factor of 2 or more. I can try for a factor of 2 or more. So now your matrix is converted to by saying, bro, Aryan, bro, now you have some obstacles. Obstacles are, let's say 1, 1, and let's say here is 1, or let's say here's 1, here is 1. For a safest, again, 1 is a thief, but now I'm saying, let's say okay, 2. This is the obstacle right now. You can only go on to 0 cells. So this, okay, 2 will reflect, but let's say hash, sorry, I'll change it, but yeah, say hash. So what will happen right now is your task is to simply traverse from this cell to this cell, only traversing the 0 cells and not touching hash. If without touching hash, you can reach your last cell, which means you actually have a path which validates this safest factor. And how you build this hash? You build this hash by saying that, bro, this hash is simply if my distance to the thief, if it is less than my safest factor, which means it's a hash for me, it's a obstacle for me, I cannot go on to this cell altogether. I can own if I've assumed my safest factor right now to be 2, so I can only stand on those cells whose safest factor is more than or equal to 2. That's the reason I can only go on to those cells whose distance to thief is actually more than equal to my safest factor. And again, this I'm trying starting from 0. Okay, I'm saying, okay, safest factor in the very beginning is 0, which means nothing. Then maybe 1. Okay, which means I can accommodate a distance of 1. 2. I can accommodate a distance of 2. And again, when I say 2, it is 2 or more. It is 3 or more. It is 4 or more. When I say 2, it should not be less than 2. The distance should not be less than 2. The distance should be more than 2. It can be more than 2, because you can see for this, the distance is 3. For this, the distance is 2. But this is a bad index, a bad set, because its distance is 1 and my safest factor is 2 right now. Cool. So that is the only thing which we will do, that we'll simply do a traversal, and while traversal, we'll simply check that the pre-computed thing which we have done and which we did earlier, pre-computation, which we did earlier, that pre-computation should make sure it is more than equal to my safest distance. What is the complexity right now? Because of you have to maximize it, you will try from a smallest safest factor and you will try and increase gradually. And we know that in worst case it can be n plus n, which is roughly n complexity. So you will try for all the safest factor, right? Then at every, but Aryan, when you are maximizing at a safest factor of 2, you are saying that it is allowed to actually increase. Actually, it is allowed to have a distance to thief as 2, 3, 4, 5, and so on and so forth. Then why you even need this traversal? Because, bro, if you are saying that if you are, let's say, at 3 is a big number. If I am saying if I have a matrix and this is a cell and this is a thief, distance is 3. Okay, there can be a chance that you might try for a 2. Okay, like let's say you said, okay, the distance is 3, but what if I can maximize my distance? So I have to keep on trying. I have to keep on trying and stretching my limit that I'm maximizing my safest factor, right? Okay, so it will be n, and for every of this safest factor, I realized I have to traverse in the entire matrix or the grid. That is again a BFS or DFS traversal, which will again take O of m into n time. But for every traversal, we realize that we need to pre-compute this distance to thief matrix, which will be done by simply doing a multi-BFS traversal from the thieves. Okay, that is simply a pre-computation. That's the reason I have added this. So my ultimate complexity will become n into m, which will be O of n cube. And if we look very closely, we can optimize this. How? Because it is gradually increasing. So, okay, it will be possible that a safest factor of 0 is possible. Okay, 1 is possible, 2 is possible, 3 not possible, 4 not possible, 5 not possible. Because 3, if it is not possible, which means I don't have a path whose every cell is actually having a minimum distance, having a distance to the thief as 3. If that is the case, for sure I will also be I'll also not have the path which will have every cell distance to thief as 4 or more, I'm saying. So if it is not even possible as 3 distance, how can I have more distance? So this pattern is called as binary search, where something is right and then wrong. So I realize I can simply apply a binary search, which can actually ultimately reduce this O of n to O of log n, ultimately making us reach to a complexity of O of n square log n. Cool. Now let's see the code. I've actually explained everything, what every part of code is doing, but this is the ultimate crux. In this, you learn multi-BFS traversal and a lot, okay? And again, a simple traversal, which you can do simple by BFS or DFS. Now, let's see. First, in the very beginning, we realized we have to pre-compute something, which is distance to thief. For that, we realize we need to push all the thieves in the queue. So, I will simply have a queue, because we know that these are the coordinates. So, we'll take the pair. Now we'll go on to the, we simply make a visited and the distance array. This distance array we needed. So as for the traversals later on, firstly, I pushed on all the thieves. If something is a 1, that's a thief. I will firstly make it as visited and then push that thief in my queue. Because I know I will start doing my BFS traversal from my thieves. Again, that's a BFS traversal because it needs to be minimum distance. Then ultimately, if my queue is not empty, get the top element of the queue, which is the current row and the current column. Okay, simply pop out. Then I can simply say the distance right now to the current row, the current column will be the length, or basically length is the level, current level, or the minimum distance you can say. And ultimately then go on to all the 4 directions. Ultimately, how we go into 4 directions? By simply saying, okay, it is a new row. Again, this thing, if you are wondering, it is simply I have defined globally. If you can see, just it is required to go on to all the 4 directions. This is -1, 0. This is 1, 0. This is 0, -1. This is 0, 1. It is saying that you will go on to all the 4 directions. Now I will get the new row, new column. This is the new row, new column from the current row, current column, right? Then I will say if it is valid. What do you mean by valid? There can be a chance, there can be a possibility, right, that it is not valid. What they mean by not valid, which is out of the grid. So this is simple function which I have made by saying that if something is less than 0 or maybe equal to my grid size or maybe visited, then it is not valid, else it is valid. So just to make sure, okay, I don't go outside the grid bounds, so it is valid. Now I will actually say I have visited this node, which is the new row, new column, and then I will push that in the queue. With this, I can simply do a BFS traversal and I can assign the distance. Again, its main task is to assign the minimum distance to thief. But you can also see I have also computed this length. This length is maximum length from a thief to any node. So I can use this also in my binary search, because if you remember, I was showing you that smallest factor of 0, 1, 2, up till what? Up to the maximum length. And while computing my multi-BFS traversal, I have also got the maximum length, so I can also use that length here itself. Okay, right? Okay. Then what I do? Okay, I'll simply have got the maximum length. Let's try simply. Low is 0, high is maximum length. Simply, this indicates the SF as 0 and SF as len. Ultimately, our simple binary search, if you don't know what the fund of binary search is, simply write on YouTube binary search by Aryan Mittal. You'll get a video. Simply watch that video. Now, while low is less than equal to high, simply find the mid. Again, L plus H by 2 or L plus H minus L by 2. It's totally up to you. Then find if this distance is safe or not, which means I am right now saying SF is equals to X. I'm trying to check if this distance is safe or not, if this X is good or not. If this is good, I will try for a higher SF. I want to maximize my SF, so I will try for a higher SF. If it is not good, I will try for a lower SF. right? And ultimately, if it's good, make sure to also populate the answer itself and ultimately return that answer. Now, your main task is your SF. When you have fixed your SF, let's check if this SF is good or not, or this SF is good or not. Now, you will come on to my SF, okay, is safe, saying that I have passed in my distance to thief because that is primarily required, and also this is the current safest distance. If you remember, I will exactly use this formula, that the distance to thief from this current to current column should be more than equal to my safest distance, which I have assumed right now, that is 2. For example, I have assumed in the example. So if I come on back, I know that I have to not simply do a BF. I have the matrix. I have to simply go from this cell to this cell. That's it. There is no concept of shortest path or like that. So in this case, you can either use a BFS or a DFS traversal. It's totally up to you. Both will work. But let's say I use a BFS traversal. So I did, again, for a BFS traversal, simply for this cell, go on to all the neighbors and then simply a BFS traversal. How we do? If you don't know how to do it, simply write on YouTube BFS traversal by Aryan Mittal, you'll get the video. Now, firstly, our prime check. We have to push all the elements in the queue. Anytime if the distance of any cell, if it becomes less than my less than my safe distance, I have to return a false. It's not possible because I can only go on to cells if its distance to thief, it should be more than equal to my safe distance. I can only go on to those specific cells. So I will go on to every cell. I'll go on to every cell and say that the distance, if it is less than my safe distance, I should return false. If not, then push that first element in my queue and then simply start traversing. Simply say make a visited, simply make the visited of the first cell as true, simply apply a simple queue traversal, get the current row, current column. If that is equals to -1, okay, you have reached your end node. Wallah, congratulations. If not, then keep on trying for all the 4 directions. For every directions, find the new row, new column. Same funda, exactly same. Find if that cell is valid or not, which means it should be in bounds of the grid and it should not be visited. Then check again for the new row, new column. If this distance is less, bro, continue, try for the next cell, next new row, new column. If yes, then visit it and then push that in the queue. Ultimately, if I have not reached at this point, which means ultimately I have finished my queue and I could not reach at this point and I have to ultimately return a false. If I would have reached here, I would have returned true ultimately from here itself. This will show me that if I am actually able to reach from this distance with this safe distance, can I reach from my start to my end? That is, this will tell is safe and ultimately it will return a true or a false for a specific safe distance SF factor, and then ultimately I can return the maximum answer because I'm maximizing my answer here. Complexity, as I've showed you, it is n square, which is n into m into log m. N square is for BFS traversal, log n is for the binary search. Again, there is a plus n square factor also, which is the pre-computation of a distance to thief vector, and ultimately I can get the space will be again simple O of n square because of simply using our distance to thief vector, visited vector, and also our BFS and BFS traversal both times, which we have done. And that's it. Cool. If you have not watched this video, just go and check the comment section below. And yeah, see you, goodbye.